How does the textbook compare to the way my handouts present the material?
Handouts are better.
What?
The handouts are pretty clear.
Okay, we need to make some progress, guys. Friedel Crafts. Friedel Crafts. Lab this week, we're doing, set to be doing the diazonium reaction with your amino. So nitro, you make the nitro, amino. Now you're going to replace the amine with an iodine by a diazonium reaction. That's in this purple handout. Also need to start getting data on products, melting points, IRs. I think some of you I'll ask to begin by taking melting point. Others, I probably, if your amine was one spot on TLC, you can proceed with the diazonium reaction. That way, when you get done, the IRs will be more open because some other people have already done that. Okay. And then starting next week, more and more, particularly next week, we'll be more open to what you want to do. Okay? But the timeline is there, suggested timeline. Okay, let's finish up Friedel Crafts reactions. Again, we need to make some good progress. We get the top one, yeah. The second one here is an example of a intramolecular reaction. If I get a product here, see this?
Yeah.
What did you get here?
There's a 5-member ring that's formed.
A what?
A 5-member ring.
5-membered ring is formed. 1, 2, 3, 1, 2, 3, yes. Product here is going to be one, 2 carbonyl. Yes, that's a 5-membered ring. We're going to coordinate. We're going to lose this. We're going to make the acylium ion. What type of director is this here? Bonding to the ring. Ortho para. Well, it has to be ortho. There ain't no way that this is going to bond over here. Actually, it could if that was long enough. It might could. You could get something fancy. But the closest position is for right here. This to attack the acylium, make carbon-carbon bond right here. You should be able to do this mechanism. It's just an example of intramolecular Friedel Crafts acylation. Yes.
Like if it was long enough to go around, would that just be really unstable or trying to be unstable?
Well, if it was really unstable, it probably would be less likely to form. I'm just saying, it's going to be ortho because it's here. But indeed, this is an ortho-pair director, so it is directed here. It's going, okay, again, hard to react here, but there's always some unique reaction out there. Okay, one's below. What we got going on here? An alcohol, sulfuric acid, carbocation, product here. What type of director do we have on this ring?
Ortho-pair.
Yeah, it's an ortho-pair director. How about this here as a product?
Yes.
Plus ortho.
Yep.
Don't make tert-butyl carbocation. This attacks EAS mechanism. Friedel Crafts does tend to prefer para, but we may also get some ortho product. I'll just show this as ortho. Okay. Ortho para, you're going to have to. If you get mixtures, you're going to have to purify and separate. The mechanism gives you both, unless there's something going on. Down here, HF, can we get a carbocation? What can we get here?
Yeah,
looking for carbocations. We can make this carbocation. New H here, yeah? Yeah.
Mm-hmm.
And then the ring can attack, yeah? And get you your, boom, Boom. We're going to add this group para. Just made this bond. These electrons came this way, leaving this as plus. Yeah, good old EAS mechanism, but the ring attacked the carbocation. You got to know what you're leaving here. You can do resonance, but you don't have to, unless the question on an exam says you should show resonance.
Would it more likely attack the alcohol instead of, if you protonate the alcohol, wouldn't that change its directing?
You can protonate that, but that alcohol, okay, you're talking about directing. I thought you were going to talk about the reaction. Protonate here, is that oxygen going to leave?
No, it's
No. So you're not going to make carbocation there, which was I thought you might be originally talking about.
No.
Yeah. So you can protonate, but it's not going to do anything, so it's an equilibrium. It's sort of like Friedel Crafts. Doesn't work with analysts because those you protonate and it's a strongly basic, and apparently it's just the equilibrium just favors the protonation. With oxygen, you can do any acid-related reaction is okay because oxygen is just not basic enough. Remember, anytime we protonate, when we protonate oxygens, that equilibrium is very poor. And we only maybe protonate 1 in a million or a gazillion. But it can go that way. The equilibrium can be very bad. Okay? Like this is where you want to go. It can be very bad. It can be like this. You're just not making much. But in a mechanism, if this continues on and goes somewhere else, then this equilibrium will just adjust. And even though it's bad at a single point, it will adjust and you can go through there. But if this doesn't continue on, for example, that oxygen is not going to leave, then this equilibrium is just bad and it sits over here. And so, this is a practical thing that we don't often talk about. Okay, so you just lose proton, right? There's an H here, you take it, you go. Basically, you're putting this group either ortho or para, you can finish it up. Basically, another way to make a carbocation. A couple of examples here. This is a synthesis of, I believe, Cataract, an anti-acne medication. Synthesis, look at 16 to 17. What type of reaction are they doing? It's essentially an intramolecular Friedel Crafts alkylation. But they're reacting what here? Alkene, acid. Okay? H3PO4. Strong acid. No, it's not classified actually as strong acid, but it's pretty strong. It's strong enough to do the chemistry. Alkene, where are you going to make cation, left or right?
left.
Right.
It's going to protonate, just like we protonated right here. You're going to make cation here, then the ring attacks that cation. That's how you get this bond made. Okay? What's a carbocation reaction? Alkene carbocation. It's just blending alkene chemistry with EAS chemistry. Okay? The P2O5, that reacts with the water and the phosphoric acid to make more phosphoric acid. It serves to make the phosphoric acid more concentrated. Because when you buy phosphoric acid, it's usually 85%. But there's tricky ways to increase that concentration, and that's what the P2O5 is. And so apparently they needed to be more concentrated than just 85%.
Why is it sold at 85%?
Certain things are sold at certain, like HBr when you buy it is usually 40 or 60, I can't remember. Certain acids just come in certain
Is it just a
concentration
thing?
Do what?
Is it just a safety thing?
It could be safety, like hydrogen peroxide is sold no more than like 30 or 35%. Otherwise, it could be sort of a practical thing of how it's made. It's just easier to get a 40% solution. Certain things. I mean, concentrated HCl comes as 12 molar. Why? Because that's about as much water. HCl is a gas. You pump it into water as much as you can, and then it won't hold anymore, and it's about 12 molar. Now there we're classifying concentration on molarity. Here it's a percentage. But even sulfuric acid is a certain percentage because sulfuric acid just will not exist pure. That's a very practical question where I wish we had tons of time. That's the essence of chemistry and why things are done this way. And it's often, you just have to ask, but and it comes from just experience and over time to learn things. Look at the next reaction. What are they doing in the next reaction? 17 to 18. It's a Friedel-Crafts acylation. They're using tin chloride. This is the Lewis acid. Analogous to AlCl3. Tin 4, good buddy. Tin 4 chloride. This is tin 4, Lewis acid. It's not as strong as AlCl3, but it's often sometimes used. This is benzene, phenyl with an H. That's a designation of this benzene solvent. Which is kind of interesting because benzene can actually be acylated here. Benzene is a solvent that could react. It's a little surprising. A lot of times you see nitrobenzene used as a solvent because nitrobenzene won't do Friedel-Crafts. It's interesting that they use benzene. But they're also doing room temperature, so it's very mild. And what type of, which is more reactive, benzene or this ring?
That one.
Why is this ring more reactive than benzene?
It has a director.
Because it has two activating groups, one alkyl and one sulfur with a lone pair, group 1. Which one's going to direct? The alkyl group or the sulfur?
Sulfur.
Sulfur, because it's a stronger activator. Sulfur is what type of director?
Orthopara.
So ortho or para to the sulfur, what did we get here?
Para.
Here.
Para. Now that doesn't mean they didn't get any ortho because they're not given a yield here. Maybe there was also some ortho in the mixture product and they had to purify it out. But again, a lot of times these carbocation reactions prefer para. Alright? So that's just another, it's like back-to-back Friedel-Crafts. One from an alkene to make the second ring, then they're putting on the acyl group. You don't, this is a little fancier chemistry, converting this to an alkyne. A little bit fancier. The only other thing on here you might know is down here. This is 1,2. It says then 1 and 2. What is N-butyl lithium going to do to this?
Takes the H off the alkyne.
Very good. We've got that slightly acidic H out there. That's an acid-base reaction. The N-butyl lithium is making the anion out here, because that's the most acidic H in the molecule. Then this reacts with the zinc chloride, and they're making, that's an organometallic. Okay? Actually, this last reaction is a Nobel Prize-winning reaction where you use palladium, and you will use palladium in the 8-week lab. There's a reaction. That's called a Negishi. A Negishi reaction. You can look that up on YouTube if you want. Or not YouTube, but Wikipedia. Okay, using organozinc, coupling reaction. Negishi was a chemist at Purdue. Probably still there. I think he's still alive. Really active in the 70s and 80s. And that general reaction won Nobel Prize in like 2010. Negishi shared it with a couple others, including Suzuki. And the Suzuki reaction is the one that's in the 8-week lab. They're all palladium catalyzed reactions. Very important chemistry these days. Okay, this last one is a synthesis of Vioxx. It used to be a billion-dollar drug, anti-arthritis drug, but it had to be pulled because it caused heart problems. A lot of sad people. What's the first step in the synthesis of this? Freedom crafts, para to the sulfur. Then they're oxidizing the sulfur. You don't really know that reaction. The next one, though, we'll see during test 4. I'll show you this handout again. What's coming next, though?
SN2?
Just a good old SN2. They come in here with this carboxylate anion, and it kicks off the bromine, and that's how they're making that bond right there. Good old classical SN2. But getting the bromine on is important. We'll be looking at carbonyl chemistry and doing that during test 4. The next reaction we'll also see during test 4 called an aldol condensation. Okay? So it's a very doable, understandable synthesis here, particularly after we get through test 4 near the end of the course. All right? But the first step up there is a Friedel-Crafts. Those reactions leading to a compound like you would make in the lab, but that compound is generated $1 billion in sales. Okay. If you can only make something and generate $1 billion. But what you have to do is you have to design and then create, synthesize a new molecule that has some activity, that either drug activity or maybe it's active as a material or some other thing. Okay, I gave you the other color, the yellow, before, but I think I want to do the purple today first. For one reason, because it includes the Diazonium Chemistry, which we'll be doing this week. May not get to it, but I want to kind of get through this, I think, first. Now, I also gave you earlier an outline of all this material. That outline is there. Hopefully I'm hitting each mark of the outline, but it's for you to sort of be organized. All right, see what we're doing. But I'm sure on the other outline it's going to say something about benzylic chemistry. And the first thing we can look at is benzylic bromination, a very common reaction with aromatics. But we're looking over here though, not the ring. But the carbon bonded to a ring is called a benzylic carbon. We saw that in Organic 1. Great place to make a carbocation. It's also a great place to make a radical. A very common reaction if you have a benzylic carbon, like a methyl or even longer, that's a benzylic carbon, is to brominate by a radical mechanism. You can do this with bromine. Okay? But you want to have light. Very common radical bromination. You got to be careful here though, because bromine we can also do an EAS. Right? Toluene. Methyl is an ortho-para director. Couldn't we also do this chemistry?
Mm-hmm.
Yes. Both are possible. But here's sort of what you want to look for. When you do an EAS, you're going to have a Lewis acid catalyst. And that's sort of like, hey, we're doing the Lewis acid, this is EAS chemistry, okay? When you do the radical bromination, you're going to have the light that's sort of there. Or maybe a peroxide, which is known to be a radical initiator. Yeah.
Is this the same thing we covered at the end of Orgo 1?
Exactly. We've covered this before. Pointed it out here because it's very common in the reaction of aromatics. Yes. Exact same thing. That's why I'm not really going to go over the mechanism here, because you should have seen the mechanism before. In the Organic 1. Did you guys in other Organic 1 see radical? Okay. And also, instead of using bromine, we can use NBS, remember, as a source of bromine radicals. You guys see that, Organic 1? NBS? Okay? NBS here, source of bromine radicals. Same thing with the light, this can homolytically cleave. All right? Instead of producing 2 bromine radicals, you produce a nitrogen radical and a bromine radical. The difference is this is a nice solid that you can weigh out, where bromine is a very volatile liquid that if you open the lid, it's going to be right there in your face. If you spill bromine, you're going to have to evacuate the lab. If you spill NBS, you get the broom out and sweep it up. A little bit more safer and convenient. It's a convenient alternative to elemental bromine. Now, this doesn't have to be radical. These things can be ionic and do sort of ionic EAS mechanisms. Some of you used NCS for the sulfanilamide. Wayne, you used NCS. Chlorine here instead of bromine. But that was more ionic. You can attack this halogen and kick that off. This is more prone to leave if you got acid. If you protonate something over here and this leaves. That's why you used acetic acid in that reaction. Okay, so it's a reaction to remember. 2 examples there. The first one, just toluene. The second one, basically, where's the best place to make radical over here? Right there, benzylic, because it'll be resonance stabilized. And we did resonance of radicals in organic 1. You should be able to draw a resonance structure of a radical. This reaction is also usually only bromine, because a chlorine radical is going to form radical here anywhere. Bromine's more selective. If you try to do chlorination, that chlorine radical, what does it take from this molecule?
H.
Takes an H. Because up here we're going to make this plus what?
HBr.
HBr. The bromine radical strips out an H. The chlorine radical takes an H, leading to a radical here. But it's going to take just about any H. It can take any of these H's. It's not going to be as selective. The reason it takes any of them is because it's more reactive. Like the bull in the china shop. It's just, here I come, I'll take H's. I'm so reactive. And the chemistry is just so fast that you lose the selectivity. Bromine has just the right thermodynamics. And then iodine is too lazy. Iodine is not reactive enough. The iodine compounds, if you remember from Organic 1, I told you that they usually go backwards. Okay? So yes, for me, this was covered at the end of Organic 1. You have your handout from Organic 1. Very important reaction here. In my examples, I just did mono. Just as a side note, you can do here, you could brominate twice. Occasionally you may see that. But probably not in your testing format. Usually stick to that. Why would you want to brominate? Do a benzylic bromination? Because now you have a good leaving group, right? And now you can come in with something like KCN and you can get what type of product?
Something with the cyano group?
Yeah, you can just do a substitution and now you can do a good old SN2 out there. Or we could come in here with potassium terbutoxide. What type of chemistry might we be doing here?
Elimination.
Donald, what type of chemistry are you doing here? Strong base. Could be a nucleophile, but the terbutyl is classically there for what reason?
E2 elimination?
Make it sterically hindered. So we have a sterically hindered strong base. What type of mechanism does this seem like we're doing?
E2.
E2. Yeah. Product here, what do you suggest?
An alkene? And the carbonyl? Okay.
Up here, SN2, here, E2. These look like right products?
Mhm.
I drew trans there. There's two H's here. We don't have to worry about anticoplanar, because one of them will be. You got two choices. When you have choices, I think you prefer to show the trans product. There's only one place to eliminate is right here. So you don't have any Hoffman or State cells, right? There's only one place to put the double bond. The only choice is the product going to be E or Z, right? Multi-step synthesis. Somebody have a product for this? Probably not, because I just gave you this handout 5 minutes ago, right?
Yeah.
Okay. If you had this handout from before, you would have already worked this and had a good suggestion of what this would be. Somebody have product? Multi-step synthesis. We will see multi-step synthesis on test 2. I did a little bit test 1, and I didn't really put a dedicated multi-step synthesis on test 1. What do we got here?
So Frito crabs.
And ortho meta.
First is Frito crabs. I'll just sort of do it, and I'm going to erase. Step 1 gives that. Everybody agree?
Agree.
What's the name of that compound?
The
Acetophenone.
Acetophenone. Then we're going to brominate. Where's it going to brominate?
Meta to it.
Meta. That's a meta director. Okay. What's zinc mercury HCl going to do?
Reducing agent, or
It's the,
it would reduce the ketones.
Clemenson reduction. Clemenson reduction. Get rid of the oxygen. Deoxygenation. That remains a 2-carbon. It's now an ethyl. NBS. H nu. Benzoic bromination. There we go. We can finish this up with maybe some type of nucleophile.
Yeah.
We can keep going. If you put in a nucleophile, what could happen?
What about substituting? Is it easy? We'll just substitute with like SN3. It's easier than or.
No, just basic nucleophile. We're going to react here.
yeah.
If we're doing SN2, or
I know you haven't covered it, but on the sheet, what about the nucleophile aromatic attack?
we'll be doing that. But you know, if you're doing SN2, that ain't SN2, because SN2, the leaving group has to be in what type of carbon? Tetrahedral. Only one of those bromines is on a tetrahedral carbon. You're not going to displace this bromine by an SN2. But yes, you can displace that bromine by some other mechanism, which is on the other handout. You can do a substitution with the other bromine, but it ain't SN2 or SN1. We'll have new substitution mechanisms. Okay? But ultimately, we could keep going there. There could be other steps there. There's more of that in the back of this handout. Please be looking at that. In the back. Starting with benzene, provide a synthesis of the following. Okay, please be looking at that. We will hit that next time or at some point. I gave you a little prelude to that. Okay. Let's be number 2, benzoic oxidation number 2. Or number 2, benzoic oxidation. Not benzoic bromination, but oxidation. The benzoic carbon can be oxidized to a carboxylic acid. Wow, how? I imagine how. Okay. First off, it can be done. Is this an oxidation? How many bonds to a more electronegative atom? 0. How many bonds to a more electronegative atom?
2,
3.
3.
It's an oxidation. You need an oxidant to do an oxidation. Everybody agree? What oxidant can be used here? The big 3. The big 3 will do this. Remember the big 3? KNO4, chromium trioxide, or
K2C.
sodium or potassium dichromate, which those last two both form chromic acid. Yes, but KNO4 is the most common with benzoic oxidation. KNO4, you get the carboxylic acid. Mechanism, not going to look at it. It's probably a radical oxygenation as opposed to a radical bromination. And it's probably multiple. That is, we can envision, instead of putting like 3 bromines on this carbon, how about 3 oxygens? Like the OHs. Possibly this is mechanism. And then this, what does this have to lose to get this? What elements or compound does that have to lose to get the final product?
Oh, water?
Yes, water. This just loses water, and you end up with a double bond OH. Okay? So it's probably like a full radical oxygenation, and then it just loses water. And that's all the mechanism I'm going to give you. It's a common transformation, oxidizing it. Okay. Now, very interestingly, if you've got more than one carbon, you also get the carboxylic acid, the benzoic acid. Here we lose 2 carbons. These carbons are most likely lost as CO2. And since there's 2 here, probably it's 2 CO2, although I'm not 100% certain it's 2. It's at least 1. If it's at least 1, it's got to be 2. So that's the fate of the other carbon. It will chew them off and spit them out as CO2. And you'll get the benzoic acid here, just like we got up there, where it was just started with 1 carbon.
Dear Stevens, does that hold true if there's like 10 carbons? If it's
Yeah,
10 carbons?
this could be 100 carbons long. It'll chew them all off.
Just give 1 carboxylic.
Because what it does is it first probably doubly oxygenates here. But then there's some chemistry that apparently takes place where it cleaves this to give a 3rd one. And once it gives a 3rd one, then it's just like the original. And again, we're not looking at the mechanism there because it's probably radical, and those are very hard to know mechanisms. There's some reactions in organic chemistry where the mechanism is just sort of not quite defined, not well defined. But we know it's a very common reaction that gives a high yield of a product. And this is a very common transformation that we need to know. But not only that, it's a good way to make a carboxylic acid. So your toolbox of reactions, great way to make a carboxylic acid. But it's going to be a benzoic acid. It's going to be, right, it's benzoic acid. Now important here, it was actually said on the first page, both of these reactions, radical bromination and radical oxygenation that we're doing here, both of these reactions require at least 1 benzoic hydrogen. Product down here.
You would have a carboxylic acid on the bottom.
Yep. Plus 1 CO2, because 1 carbon is lost to CO2. Why no chemistry over here?
There's no benzoic H.
It's a benzoic carbon.
But there's no benzoic H.
No benzoic H. You got to have a benzoic H. That's known here. Of course, in the benzoic bromination as well, you're not going to be doing a radical reaction there because there's no H to abstract. All right? Why is benzene so toxic? It's a carcinogen, but toluene, much less toxic and not a carcinogen. Because benzene, if it gets in the body, it will localize in fatty tissue. And it'll stay there. And it can do reactions that we will never talk about. Oxidation reactions. Toluene, though, if it gets in the body, the methyl will be oxidized because the body is a lean, mean oxidizing machine. It doesn't use KMNO4, but it uses enzymes. And this group is oxidizable. And when it becomes the acid, in certain pHs in the body, it actually exists as the carboxylate anion. And if it's existing like this, it's quite water soluble. And since it's water soluble, it's easier to flush it out of the body. Where again, benzene will never do this, and benzene will just hide in your fatty tissues and start causing lots of problems. Okay? This is called a metabolic handle. It's a place in the molecule that can be metabolized. Metabolic handle. All right? In pharmacology, you may hear that term. Talk about drug metabolism. Benzene has no metabolic handle. All right? Multi-step synthesis. I'm trying to get you ready for the last page. Do we know how to make benzoic acids?
Yeah. From alkene.
Does it have to be a methyl, or could it be an ethyl, or
Yeah.
a butyl?
Just use Friedel craft.
Right. It could be alone. Okay. It doesn't have to be a methyl. It could be an ethyl or propyl. Or, okay. Important with those there is sequence. What do you want to put on first? Because once you put one thing on, it's going to have directing effects. You want your two groups pair up. So you need a pair director somewhere.
So Friedel craft, probably.
You got to think about your sequence of reactions. All right, think about that. All right, the next reaction, and we're out of time, but it's one you're doing in lab this week, is the Sandmeyer reaction, or Diazonium Chemistry. This is from another textbook or lab book from anilines. The amine on the benzene can be converted to a diazonium, 2 nitrogens. The diazonium can serve as a leaving group and be replaced. Now again, it ain't SN1 or SN2, but it is a substitution mechanism. In this case, it's probably radical again, which is hard to show. Please be looking at this. This is the reaction you're doing this week in lab. So you have the amine. You're going to make the diazonium using nitrite, sodium nitrite. Then you're going to use Ki to bring in the iodide. Okay, guys. Video key will be posted later today. Now this is not exactly benzyl, so it's not a benzylic carbon. But the reason it's in this handout is because we're looking at something bonded to the ring. It's not carbon, it's nitrogen. Something bonded to the ring that we're doing chemistry on. Okay, guys.